Welcome! Today, we'll dive into LeetCode problem number 1665, minimum initial energy to finish tasks. This problem is all about optimizing energy management while meeting task constraints. We'll explore the problem requirements, break down the solution, and discuss how to implement it efficiently. Let's get started. In this problem, we are tasked with determining the minimum initial energy required to complete a set of tasks. Each task is represented by a pair, actual_I, minimum_I. Here, actual_I is the amount of energy consumed to complete the task, while minimum_I is the minimum energy you need to even start the task. The key is that your initial energy must always be at least minimum_I before starting any task. Once you complete a task, your energy decreases by the actual_I value of that task. Importantly, you are allowed to complete the tasks in any order, and your goal is to find the smallest initial energy that makes it possible to finish all the tasks. The function will take an input tasks, which is a list of these task pairs, and return an integer representing the minimum initial energy required. Let's explore an example to understand this better. Consider the input 1, 3, 2, 4, 10, 11. The output is 11. Here's why: if you start with 11 energy, you can complete the tasks in this order. First, you do task 2, which requires a minimum of 11 energy. After completing it, your energy decreases by 10, leaving you with 1 energy. Next, you complete task 1, which requires at least 3 energy. Since you only have 1 energy left, you wouldn't have been able to start this task earlier. However, with an initial energy of 11, you would have had enough to meet this requirement. After task 1 is completed, the energy decreases by 1, leaving you with 0 energy. Finally, you complete task 0, which requires at least 4 energy. Again, this is why starting with 11 energy is necessary. It ensures you meet all the minimum requirements at each step. The energy decreases by 2 after this task, leaving you with 0 energy again. So, the minimum initial energy required here is 11. Now, let's look at another example with the input 1, 2, 2, 4, 4, 8. The output for this case is 8. To achieve this, you can complete task 2 first. It requires at least 8 energy to start, and after completing it, your energy decreases by 4, leaving you with 4 energy. Then you move to task 1, which requires 4 energy to start. After finishing it, your energy decreases by 2, leaving you with 2 energy. Finally, you complete task 0, which requires 2 energy to start, and after completing it, your energy decreases by 1, leaving you with 1 energy. So the smallest amount of starting energy that allows you to complete all the tasks is 8. Finally, consider the input 5, 5, 2, 10, 3, 15. The output here is 15. To minimize the initial energy, you begin with task 2, which requires 15 energy to start. After completing it, your energy decreases by 3, leaving you with 12 energy. Then, you move to task 1, which requires 10 energy to start. After finishing it, your energy decreases by 2, leaving you with 8 energy. Finally, you complete task 0, which requires 5 energy to start, and after completing it, your energy decreases by 5, leaving you with 3 energy. Thus, the minimum initial energy required for this case is 15. To wrap up, let's consider some edge cases. First, if there is only one task, the initial energy must at least match the minimum_I for that task. For example, if the input is 3, 5, the minimum starting energy would be 5. Next, if all tasks require the same energy, you can complete them in any order, and the output will be equal to the largest minimum_I. For instance, with 3, 3, 3, 3, 3, 3, the output is 3. Lastly, for large inputs, the algorithm must be efficient enough to handle up to 100,000 tasks while adhering to the constraints. The goal is to calculate the result efficiently without exceeding the time limit. To solve problem number 1665, we need to determine the minimum initial energy required to complete all tasks while adhering to their constraints. Each task is represented as a pair, actual_I, minimum_I, where actual_I is the energy consumed to finish the task, and minimum_I is the minimum energy required to start it. First, we can consider a brute force approach. The intuition here is straightforward: try all possible orders of tasks and, for each permutation, check whether the tasks can be completed with some initial energy. While this guarantees correctness, it involves iterating through all permutations of the tasks, which takes factorial time, and then simulating the energy consumption for each order, leading to a time complexity of O(n). n. This makes it prohibitively expensive for even moderately sized inputs. While conceptually simple, the trade-off is clear: this approach is computationally infeasible for large inputs, though it does serve as a baseline for correctness. A more refined approach is the greedy strategy, which focuses on minimizing the risk of running out of energy. Here, we observe that tasks with higher minimum_I values impose stricter requirements on the initial energy. By sorting tasks in descending order of this risk factor, we aim to reduce the likelihood of failure. However, this method is insufficient because sorting purely by minimum_I or actual_I does not guarantee an optimal solution. For example, it may still result in suboptimal energy usage in certain edge cases. To address this, we move to an optimized greedy approach that sorts tasks by the cost difference, calculated as minimum_I actual_I. This sorting criterion ensures that tasks with the highest relative energy requirements are handled earlier, minimizing the peak energy demand. The key insight here is that by prioritizing tasks based on this specific metric, we achieve an order that inherently minimizes the initial energy required. The algorithm is simple: first, sort tasks by minimum_I actual_I in descending order, and then simulate task execution to compute the energy requirements. The complexity of this optimized greedy approach is efficient. Sorting the tasks takes O(n) log n, and simulating the task execution is O(n), resulting in an overall time complexity of O(n) log n. This makes it a practical solution for larger inputs. By sorting tasks based on minimum_I actual_I, we minimize the maximum energy needed at any point, ensuring correctness and efficiency. This method is chosen because it balances optimality and performance. The brute force approach is impractical due to factorial growth, and alternative greedy strategies fail to guarantee the correct solution. The cost difference sorting leverages the key insights of the problem and provides reliable results. While this approach requires a clear understanding of the relationship between the sorting metric and energy minimization, the trade-offs are negligible compared to its benefits. Ultimately, the optimized greedy strategy is the most effective and efficient way to solve problem number 1665, ensuring the minimum initial energy is calculated accurately and quickly. The problem requires us to figure out the minimum initial energy needed to complete a series of tasks, each with two key conditions: the energy consumed to complete the task, actual_I, and the minimum energy required to start the task, minimum_I. The challenge lies in ensuring that as we progress through the tasks, our available energy never falls below the required threshold for any task. The goal is to minimize the starting energy while successfully completing all tasks. To solve this, we first need to understand how these constraints interact. For instance, if a task has a very high minimum_I, it might require us to reserve a lot of energy before starting, even if the actual energy consumption is low. This introduces the concept of scheduling tasks strategically, and one key insight here is that the order in which we complete tasks significantly impacts how much initial energy we need. With this in mind, we can formulate an approach that prioritizes tasks based on their energy requirements. A useful heuristic is to sort the tasks by their energy gap, calculated as minimum_I actual_I. This represents the extra energy buffer needed for each task, and sorting by this value ensures that tasks requiring a larger buffer are handled earlier. For example, tasks with a large minimum_I but a small actual_I pose a higher risk of failure if left for later, as smaller tasks might deplete energy prematurely. To implement this, we sort the tasks in descending order of minimum_I actual_I. If two tasks have the same energy gap, we can break ties by sorting them based on their minimum_I values. Once sorted, we simulate the task completion process. We initialize two variables: initial_energy, which captures the minimum starting energy, and current_energy, which keeps track of the energy available as we process the tasks. As we iterate through the tasks, we check if our current energy meets the minimum_I requirement for each task. If it doesn't, we increase initial_energy to make up the shortfall. After completing the task, we deduct the energy consumed, actual_I, to update our available energy. This simulation allows us to determine the minimum starting energy required to complete all tasks efficiently. The greedy approach of sorting tasks by their energy gap is justified because it minimizes the maximum energy buffer required throughout the process. By addressing tasks with the highest risk of failure first, we ensure that the smallest possible initial_energy suffices. This approach avoids scenarios where earlier tasks deplete energy that is critically needed for later tasks. Instead of deriving a single mathematical formula, simulating the energy consumption during task completion provides a flexible and robust solution. This method handles edge cases, like when all tasks have high minimum_I values or when there are no strict ordering constraints. The algorithm relies on simple yet effective data structures. Tasks are stored as tuples, actual_I, minimum_I, for efficient sorting and iteration. Sorting the tasks by minimum_I, actual_I ensures the optimal order is followed. The sorting step has a time complexity of n log n, which is manageable given the benefits it provides in simplifying the task scheduling process. The algorithm implementation begins with sorting the tasks based on their energy gap, minimum_I, actual_I, in descending order. This ensures that tasks requiring the largest energy buffer are scheduled first. We then initialize two variables, initial_energy, set to 0, to track the minimum starting energy, and current_energy, also set to 0, to monitor the energy available during the simulation. As we iterate through the sorted tasks, we check if current_energy meets the minimum_I requirement of the current task. If it doesn't, we increase initial_energy to bridge the gap, simultaneously updating current_energy to the required level. After completing the task, we deduct the energy consumed, actual_I, from current_energy. This process continues for all tasks, and by the end of the iteration, initial_energy will represent the minimum starting energy required to successfully complete all tasks. This step-by-step simulation ensures that all constraints are met while minimizing the starting energy. The time complexity of this algorithm is primarily determined by the sorting step, which takes n log n, where n is the number of tasks. The subsequent simulation step, which involves iterating through the tasks once, has a time complexity of n. Therefore, the overall time complexity is n log n. The space complexity is 1, additional space since the sorting can be performed in place, and no extra data structures are required beyond the input list. Several edge cases are worth considering. If all tasks have the same minimum_I and actual_I, the sorting step will not affect their order, and the simulation will still compute the correct initial energy. For tasks where minimum_I is significantly larger than actual_I, the sorting step ensures these tasks are prioritized, preventing energy depletion. Finally, tasks with zero energy requirements, where actual_I equals 0, do not affect the total energy and can be safely ignored in terms of their consumption. Tasks with zero energy requirements, where actual_I equals 0, do not consume energy, so they do not affect the overall calculation of the initial energy. These tasks are essentially neutral, they require a minimum energy threshold to start, but once completed, they leave the energy level unchanged. By correctly simulating the energy usage and strategically sorting tasks, the algorithm ensures that all such edge cases are handled seamlessly. This completes the algorithm deep dive, demonstrating how a greedy approach combined with sorting and simulation effectively minimizes the initial energy required to complete all tasks while adhering to their constraints. This Python implementation solves LeetCode problem number 1665, minimum initial energy to finish tasks. The goal is to determine the minimum initial energy required to complete all tasks without violating their energy constraints. The first step is to sort the list of tasks based on the difference between their minimum energy required and actual energy consumed, in descending order. This ensures that tasks with higher minimum energy requirements relative to their consumption are prioritized first, reducing the risk of running out of energy later. After sorting, we initialize two variables, min_initial_energy to keep track of the minimum energy required to start, and current_energy to simulate the energy available as we process the tasks. The algorithm iterates through the sorted list of tasks. For each task, it checks if the current energy is less than the task's minimum energy requirement. If so, it increments min_initial_energy by the difference between the task's minimum energy and the current energy. It also updates current_energy to meet the task's requirement. Finally, the algorithm deducts the actual energy consumed for the current task from current_energy. This simulates the energy spent to complete the task. By the end of the loop, min_initial_energy contains the minimum energy required to start and successfully complete all the tasks. This approach ensures that the energy constraints are satisfied while minimizing the initial energy. The time complexity of this solution is O(n log n) due to the sorting step, where n is the number of tasks. The space complexity is O(1), since no additional space is used beyond the input and a few variables, making it efficient and scalable. Here, we begin by importing the necessary utilities, followed by defining our solution class and the minimum effort method. The goal of this method is to calculate the minimum initial energy required to complete all tasks. To achieve this, we first sort the tasks based on the difference between the minimum energy required and the actual energy consumed in descending order. This sorting ensures we prioritize tasks where the gap between required and consumed energy is largest, helping us manage energy efficiently. Next, we initialize two variables, min_initial energy to track the minimum starting energy needed, and current energy to represent the energy available at any given point. We then iterate through the sorted tasks. For each task, we extract the actual energy it consumes and the minimum energy required to start it. If our current energy is less than the required minimum, we calculate the deficit and increase min_initial energy accordingly, while also updating our current energy to match the required minimum. Once we have enough energy to start the task, we deduct the actual energy consumed. This process ensures we meet every task's requirements while minimizing the initial energy investment. Finally, once all tasks have been processed, the method returns the total value of min_initial energy. This value represents the smallest amount of energy needed at the beginning to successfully complete all the tasks without running out of energy at any point. The approach ensures that we always have sufficient energy for the most demanding tasks while optimizing the starting amount. By sorting the tasks strategically and carefully managing energy adjustments during the iteration, we achieve the desired result efficiently. To solve this problem, we begin by sorting the tasks based on the difference between the minimum energy required to start the task and the actual energy cost of completing it. This difference helps us prioritize tasks that require a larger energy buffer before they can be started. For the given example, tasks are initially 1, 3, 2, 4, 10, 11. Calculating the differences, 1, 3, has a difference of 2, 2, 4, also has 2. And 10, 11, has a difference of 1. Sorting these in descending order of their differences maintains the original order, 1, 3, 2, 4, 10, 11. Next, we initialize two variables, min_initial_energy, which will store the minimum starting energy needed, and current_energy, which tracks the energy we have at any point during the process. Both are set to 0 initially. Now, we process each task in the sorted order. Starting with the first task, 1, 3, we see that our current_energy is less than the minimum required, so we add the difference, 3 to 0, to min_initial_energy. This updates min_initial_energy to 3 and current_energy to 3. After performing the task, we subtract the actual energy cost, 1, leaving current_energy at 2. For the second task, 2, 4, current_energy is again less than the minimum, so we add 4 to 2 to min_initial_energy, making it 5 and updating current_energy to 4. Performing the task reduces current_energy by 2, leaving it at 2. Finally, for the task, 10, 11, current_energy is much less than the minimum, so we add 11 to 2 to min_initial_energy, bringing it to 14. Updating current_energy to 11, we then subtract the actual energy cost, 10, leaving us with a current_energy of 1. At this point, we've completed all tasks, and min_initial_energy stands at 14. With all the tasks processed, we find that the minimum initial energy required to complete this set of tasks is 14. Moving to another example, consider tasks equals 3, 5, 2, 8, 1, 4. First, we calculate the differences. 3, 5, has 5 minus 3 is equal to 2, 2, 8, has 8 minus 2 is equal to 6, and 1, 4, has 4 minus 1 is equal to 3. Sorting these in descending order of differences gives us 2, 8, 1, 4, 3, 5. We initialize min_initial_energy and current_energy to 0, just as before. We start processing with the first task, 2, 8. Since current_energy is less than the minimum, we add 8 to 0 to min_initial_energy, setting it to 8 and updating current_energy to 8. Performing the task reduces current_energy by 2, leaving it at 6. For the second task, 1, 4, current_energy is already greater than or equal to the minimum, so we don't need to adjust min_initial_energy. Performing the task reduces current_energy by 1, leaving it at 5. For the final task, 3, 5, current_energy is again sufficient, so min_initial_energy remains unchanged. Completing the task reduces current_energy by 3, leaving it at 2. The minimum initial energy required for this example is 8. In the next example, we have tasks equals 5, 10, 3, 20, 7, 15. Calculating the differences, 5, 10, has 10 minus 5 is equal to 5, 3, 20, has 20 minus 3 is equal to 17, and 7, 15, has 15 minus 7 is equal to 8. Sorting in descending order gives us 3, 20, 7, 15, 5, 10. We initialize min_initial_energy and current_energy to 0, as usual. Starting with the first task, 3, 20, current_energy is less than the minimum, so we add 20 to 0 to min_initial_energy, setting it to 20 and updating current_energy to 20. Performing the task reduces current_energy by 3, leaving it at 17. Next, we process the task, 7, 15. Here, current_energy is greater than or equal to the minimum, so min_initial_energy remains unchanged. Performing the task reduces current_energy by 7, leaving it at 10. Finally, for the task, 5, 10, current_energy is again sufficient, so no adjustment is needed for min_initial_energy. Completing the task reduces current_energy by 5, leaving it at 5. With all tasks completed, the minimum initial energy required for this example is 20. To analyze the time complexity of our solution, let's break down the steps involved. First, sorting the tasks is a key operation. Here, the sort function is used with a custom key that computes the difference between the minimum energy required and the actual energy for each task. Sorting a list of n tasks involves a time complexity of O, n log n. Next, after sorting, we iterate through the sorted list exactly once. During this iteration, we perform only constant time operations for each task, such as comparisons and updates to energy values. This contributes an O, n complexity. Combining these, the total time complexity becomes O, n log n, plus O, n, which simplifies to O, n log n. This represents the dominant term in the complexity of the algorithm. Now, let's consider the space complexity of the algorithm. First, we have the input storage. The tasks list is stored in memory, and since it contains n tasks where each task is represented as a pair of integers, this requires O, n, space. Next, sorting is performed using Python's timsort algorithm. Timsort generally operates in place, meaning it requires only O1 additional space. In rare cases, if in-place sorting is not possible, it may require up to O(n) auxiliary space, but we assume the typical in-place behavior here. Finally, the algorithm uses a constant amount of memory for variables such as min_initial_energy and current_energy, which adds an O(1) space cost. When we add these together, the total space complexity is O(n) plus O(1), which simplifies to O(n). This shows that the algorithm is space efficient. Let's delve into the best, average, and worst-case scenarios for the algorithm. In the best case, all tasks require minimal energy, meaning the actual energy matches the minimum energy for each task. Here, sorting still takes O(n log n), and the single iteration over tasks takes O(n), giving a total complexity of O(n log n). In the average case, where tasks have varying energy requirements, the overall operations remain the same, sorting and iterating through the tasks, resulting in the same O and log n complexity. Even in the worst case, where tasks have large gaps between their minimum and actual energy requirements, the asymptotic complexity remains unaffected at O and log n. For comparison, a brute force solution would involve examining all permutations of the tasks, which is computationally expensive. With n permutations and O n operations per permutation, the brute force approach has a time complexity of O n *n, making it infeasible for large values of n. This highlights the efficiency of the greedy approach. The greedy solution optimally reduces the problem's complexity by sorting the tasks and processing them in a single pass. This approach achieves a time complexity of O n log n, which is exponentially faster than the brute force method. To confirm this mathematically, sorting the n tasks using timsort contributes O n log n, and iterating through the tasks adds O n. Since O n log n grows faster than O n, it dominates the overall complexity, giving us O n log n. In terms of space, the algorithm requires O n for input storage and minimal additional space for computation, resulting in an overall space complexity of O n. In summary, this greedy approach is both time and space efficient, making it a highly effective solution compared to the brute force alternative, which suffers from exponential complexity. In this section, let's address some common mistakes that can lead to incorrect solutions. First, sorting tasks solely by the difference between the actual energy and the minimum required energy may seem logical at first glance, but it doesn't guarantee optimal results. This is because it doesn't account for the sequence in which tasks must be performed to minimize the initial energy. Instead, sorting by the minimum energy requirement ensures that tasks with higher prerequisites are prioritized appropriately. Another common error is ignoring the task order constraint. Completing tasks in an arbitrary order without ensuring you have enough energy to meet each task's minimum requirement will likely result in failure. Finally, when implementing binary search, choosing incorrect bounds is a frequent pitfall. The lower bound should start at 0, while the upper bound should be the sum of all actual energy values, as this represents the worst-case scenario. Setting these bounds incorrectly can lead to infinite loops or wrong answers, so careful initialization is crucial. Now let's look at a couple more common issues. Off-by-one errors often occur during energy calculations. When simulating the process of completing tasks, it's easy to forget to update the remaining energy after each task. Always remember to subtract the actual energy used for a task from your total energy so that subsequent calculations remain accurate. Another mistake arises from assuming that a purely greedy approach will work without proper sorting. For instance, processing tasks based only on actual energy, rather than minimum energy requirements, can cause problems. Tasks with high prerequisites might block others, resulting in an invalid sequence. To avoid this, always ensure that the task order respects the minimum energy constraints. Understanding the problem's core insights can make solving it much easier. The key challenge here is minimizing the initial energy required while ensuring all tasks are completed. Sorting tasks based on their minimum energy requirements in descending order is a highly effective strategy. This ensures that tasks with higher prerequisites are addressed first, which is critical for feasibility. Additionally, this problem fits into a broader category of resource allocation with constraints, making it comparable to other classic problems like meeting room scheduling or interval selection. Binary search is a particularly valuable optimization technique here, as it efficiently minimizes the initial energy compared to brute force approaches. Be prepared to explain why binary search is applicable and how it reduces complexity. Don't forget to consider edge cases, such as scenarios with only one task, tasks with identical energy requirements, or tasks that require more energy than their actual values. These edge cases often come up in interviews, so it's important to be ready to discuss them. There are also several related problems that share similar concepts and techniques. For example, LeetCode 253, Meeting Rooms 2, involves optimizing the allocation of limited resources, in this case, meeting rooms, based on scheduling constraints. LeetCode 630, Course Schedule 3, is another example of a greedy problem that requires task prioritization. Additionally, LeetCode 1353, Maximum Number of Events That Can Be Attended, focuses on scheduling and prioritization, which align closely with the principles of this problem. Lastly, LeetCode 871, minimum number of refueling stops, demonstrates a similar dynamic programming or greedy approach to handling resource constraints, making it another great problem to study for further practice. Finally, let's explore some alternative approaches to solving this problem. A brute force method would involve trying all possible task orders and calculating the initial energy for each. However, this approach is extremely inefficient, with a time complexity of O(n), and is practically infeasible for larger inputs. A more efficient option is a greedy approach where tasks are sorted by their minimum energy requirements in descending order. This method is simple and works in O(n) log n time but may not feel as structured as other approaches. The most robust and scalable solution involves binary search combined with a feasibility check. Here, you use binary search to minimize the initial energy, testing whether each midpoint value is sufficient to complete all tasks. This approach ensures correctness and operates efficiently with a time complexity of O(n) log max_energy. Great work! We've successfully solved the problem using a greedy approach. Remember, sorting is often key in optimization problems like this one. Keep practicing, and you'll continue to master these techniques. Thanks for watching, and don't forget to subscribe for more problem-solving content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!